Hey everyone, my name is Marcus, and you're watching Physics for Fun. So, that is literally where the fun's gonna end. We need to get back to work. So, we're gonna try our hand at this integral right here. We're just gonna describe it briefly, and then we'll get into trying to evaluate it. This guy is an integral from 0 to infinity, and it's a difference of two decaying exponentials all divided by x. So I said decaying exponentials because both the individual terms are characterized by these constants a and b. And we're going to put the condition on them that both of them are positive and a is less than b. This gives us the condition that the integrand is positive on the interval from 0 to infinity because this guy decays faster than this guy. Well, if you don't see that, you could always go for the proof by Wolfram Alpha. So, this has a lot of interesting features, and we can showcase some of them in this video. It can't be too long, but the best way to show is by doing, so let's start doing it.
Looking at this, we might not be too sure where to start, but let's just try something. How about that? We might say, hey, let's just distribute that integral into both the individual terms, see what happens. After this, we might try to multiply top and bottom by the constants a and b. This is shown in blue. The reason for this is clearly to do a u substitution. I like to think of a u sub as rescaling our variable, so in the first integral we send x to x over a, and in the second integral x to x over b. Notice that the bounds do not need to be rescaled since they're just 0 and infinity. After completing the u sub, we see that we get an integral minus the same integral. So, we know from kindergarten that a number minus the same number is 0. We have finished this integral. Super easy, right?
Okay. Obviously I'm kidding. The video's not over yet. Something went wrong, and this is the first lesson this integral can show us. You cannot always naively distribute the integral to each of the individual parts in the integrand. The integral of the sum is equal to the sum of the integrals only when the individual integrals actually exist. We get some nonlinear effects, we could say. So let's draw an analogy between some simpler examples. If we have a function f of x equals x, then f of x plus y is just f of x plus f of y. We can distribute the function to the individual parts. But now when we upgrade this function to g of x equals x squared, g of x plus y is g of x plus g of y plus an additional term which has this 2xy in it. This is the cross terms and foiling. So a similar thing happens here. I'm not saying it's the same thing. In analogy to this, we get a non-zero contribution due to the nonlinear effects, and I'm going to spoil the result right now. It's a beautiful result. I was really surprised that something like this turned out to be so simple. It is equal to natural log of b over a. So it should involve natural log, exponentials, and this a and b. These are what parameterize the problem. Now, we're going to talk about how to evaluate this integral. So let's just actually get into that and not do something wrong this time.
Alright, so let's just start by rescaling the variables from x to x over b. So this applies to the entire integral. And I know, rookie mistake, I forgot dx. Alright, there we go. dx is for everyone. We see that the constant in the second exponent goes away, and we get a ratio a over b in the first. Now let's go ahead and redefine a over b to be equal to some real number alpha. This guy right here screams Feynman's trick at us. Now, we're not going to do that because that is actually more familiar than what we're going to see in a second. I did this integral in a very ad hoc way, and I want to share that with everyone. In order to do so, we first need to look at some Taylor series. This is a physicist's best friend, and we're going to see why right now. So to make sure we're all on the same page, let's go ahead and briefly describe what a Taylor series is. Given a function f of x, we can express it as a polynomial in x, as a linear combination of powers of x, given we could find the right coefficients, c0, c1, c2, etc. Now, you might wonder how to actually find these constants. Well, we don't really have time to go into that. I wrote below for completeness how to do it. Basically, you just take derivatives of a function and evaluate it at x equals 0. We'll just take our Taylor series from God, aka Wolfram Alpha. Alright, so this is the Taylor series for an exponential function, the one we have in our integral. We'll only need the first two terms in the end because we're going to look at small x values. X squared and everything higher is just going to be very, very small. The kth terms written out for completeness, we will not need it. Now we're going to divide by x to get the functions within our integrand. So just take that Taylor series, divide by x, you get this. Now this expansion for this function actually goes by a different name. It doesn't have a Taylor series, it has a Lorentz series. If we notice, the summation goes from n equals -1 to infinity instead of 0. There's a negative exponent. So this is called a Lorentz series actually here. We're going to rewrite the expansion as 1 over x minus a plus terms of order x and higher. That's what this O of x notation stands for. Let's also write out the Lorentz series for e to the minus b of x over x. Again, we're going to use that O notation where this O is dangerously close to a sigma. Now we can just take a difference of the two Lorentz series and we're left with b minus a plus terms of order x, where this O is dangerously close to theta. Let's just note that the divergent parts, the 1 over x, actually cancel each other. So when we go to x equals 0, we get a finite number b minus a, reassuring us that this function is integrable. Okay, so that was just a warm-up getting us used to Lorentz series. Now we're going to evaluate this integral by defining a sequence, I of n, which is exactly what we had before, but the lower bound is 1 over n. We'll say I is the limit as n goes to infinity of the sequence. Now, the purpose of doing this is it allows us to use the linearity of an integral since we don't have 0 as a lower bound this time. Let's rescale variables as x over a and x over b. The rescaling of our integrals is exactly the same as before, except the lower bounds are now rescaled as well. Notice we multiply by a and b instead of dividing by. The next crucial step is realizing that the lower bound on the first integral is less than the second, since a is less than b. We can split up the first integral as shown in blue here. After cancellation of certain terms, we end up with the final result right here. Now, since we're going to be taking the limit as n goes to infinity, these b over n's and a over n's are small. We might as well replace this function with its Lorentz series. Now, we're only going to look at the first two terms in this Lorentz series and just use that O notation for the higher order terms. When all the dust settles and you integrate the first two terms, which are fairly trivial, you end up with an expression on the last line right here. Finally, we just need to take the limit as n goes to infinity, and we see that the terms of order 1 over n and higher drop out, so we're left with natural log of b over a. You might be a little bit fussy about this step, and you should probably use induction here, but we're going to argue by proof by right answer. That's a physicist's favorite proof right there. We could also use Wolfram Alpha if we really wanted to. So QED, quantum electrodynamics, we're done.
So I hope that was satisfying to you. This is admittedly not the easiest way of getting this result. Of course, Feynman's method over here would be simpler, but in a lot of ways this was more of a Taylor series video than an integration one. Now, it's a very ad hoc method. I honestly don't know where you would be able to use this again, but Taylor series themselves, this is one of the reasons they're a physicist's best friends. Those are useful in a lot of places, even if the method itself seems kind of ad hoc. You can do Taylor series with functional integrals. That's how Feynman's rules can be deduced, for instance. Past that, there's these famous equations, Landau-Ginzburg equations. You have something called an order parameter, which tells you when a symmetry's been broken, and you can expand a free energy in terms of them as a Taylor series. With this, you can make a lot of predictions in a phenomenological way. I know that was a lot of words, and maybe it didn't make much sense, but the key point is Taylor series are useful. Now, another upside to not using Feynman's method is now I can assign homework to everyone. I want everyone to solve this integral using Feynman's method with differentiating under the integral sign, and it's due in, let's say, 2 days. So, get to work, everyone. Okay, of course I'm just kidding again. You don't have to do homework. But if anybody's interested in doing this problem, I put a little solution right here. Good luck figuring it out. I don't have time to explain any of it, especially these bounds. Those are kind of tricky, so it's just showcases further that this integral is a prime example for the use of just Feynman's trick. So in the end, you want to evaluate I of a over b, which you can show is natural log b over a just from this analysis over here. But yep, that concludes the video. I should take this time to thank 3 Blue 1 Brown for actually putting this out. This is a great opportunity for a lot of people, and he's going to change some lives in more than one way for content creators and people who view those content creators. So thanks for the great math videos and for this opportunity. Oh, and also check out the budget of Physics for Fun. My tripod's literally a real analysis book with some shoes it's mounted on. So hopefully biggest budget doesn't win here. All right, take care, everyone.